Hello, right now I'm going to be talking about 6 variables that are linked to the second law of thermodynamics, which the second law of thermodynamics basically implies that for every energy transaction, some energy is lost to the surroundings. In other words, you can say that any spontaneous process increases the disorder of the universe, and that disorder is in fact entropy. So we're going to go straight in and look at entropy, which is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. So to simply put it, it's the dispersion of energy, the spread out. And when it's dispersed, it moves in a fashion that is more disorderly than orderly. So if you were to look at a glass of water next to a glass of ice, you might think that the glass full of ice is in more disorder than the glass of water, but there isn't many arrangements for the glass of water to move through. So if you were to look at you have some water, and then you have some blocks of ice, you say. So you would think that it would have several different arrangements for it to move through, but because the state that the ice is in, it doesn't. Where water, it kind of moves more freely and has a vast amount of arrangements that it can move through. So mathematically, we can look at entropy as the Boltzmann constant times the natural log of W, where W is the number of energetically equivalent ways to arrange components. And this arrangement isn't a sort of randomness or chaos, it's the disorder, and it's also ignorance because it's what we do not know. So I'm going to go ahead and next we're going to touch on the equilibrium constant for concentration. Now the equilibrium constant for concentration is the ratio of the concentration of the products to the concentration of the reactants. And if you look at the basic setup for a chemical equation that is reversible, you have A plus B that goes to C plus D, where A plus B, A and B are the reactants, and C and D are the products, and those are their coefficients, which are basically this stoichiometric coefficients. And you can see that K, the equilibrium constant, is equal to basically the products over the reactants. So this will touch more on when we link the equilibrium constant to Gibbs free energy. But if you just keep in mind that when K is less than 1, the reverse reaction is favored, meaning reactants are favored. And when K is equal to 1, neither products or reactions are favored. And when K is greater than 1, the forward reaction is favored. So again, we just here, you can see we have the still we're talking about equilibrium constant, but now in terms of partial pressure. So instead of looking at it in terms of concentration, which is molarity, moles over liter, we're looking at in partial pressure, which is in atmospheres. So it's essentially the same thing, just now it's the partial pressure of the products over the partial pressure of the reactants. And mathematically, this is how it is derived, where we still consider the equilibrium constant for concentration, just in applying the rate for ideal gas and the temperature of that certain reaction that is taking place to the nth power, the change of the nth power, which is the n is essentially the moles or the stoichiometric coefficients, with the difference between the products minus the reactions. So now we're going to look at standard change in free energy, which is noted as delta G standard right here, and it is the change in energy associated with a chemical reaction that can be used to do work at standard state conditions. So when we talk about standard state conditions, we're referring to when P is equal to 1 atm and temperature is equal to 298 degrees Kelvin. So these are your standards. But in most cases, reactions do not take place in terms of standard conditions. They're very far off from standard. So moving on, we're going to look at, still looking into Gibbs free energy, changes in Gibbs free energy, just not in standard form. It can be defined as a thermodynamic function that is proportional to the negative of the change of entropy of the universe. So as I go forward, and I will be linking Gibbs free energy to entropy because they very much will go together. Gibbs free energy as a thermodynamic function is proportional to the negative change in entropy of the universe. So when we get into Gibbs free energy and entropy, you have to look at spontaneous reactions and understanding spontaneous reactions, because the second law of thermodynamics states that any process, spontaneous process, increases the disorder of the universe. So and lastly, we have rate constant, where the reaction rate coefficient that quantifies the rate of the chemical reaction is basically dependent on reaction order. If you're familiar with reaction order, it's zeroth order, first order, which is usually decay. We watch a reaction or a process decaying, and then second order. So if you take the rate law that comes with reactions, it can be derived so that the rate constant is equal to the rate divided by the concentration to the nth power. So I'm going to start by linking the equilibrium constant to the rate constant and work my way up towards entropy. So the equilibrium constant K for reversible reactions and rate constant K for forward and reverse reactions have a very simple relationship, as you can see. So if we look at the products, reactants A and B, reversible to product C plus D, we can say that the rate of the forward reaction is equal to the rate constant times A and B, while the rate of the reverse is equal to the rate constant of the reverse times C and D. So it's easily saying that the system will reach equilibrium when the rate of the forward is equal to the rate of the reverse. So if you were to rearrange the rate law for forward and reverse reactions, in terms, you will get the law of mass action that will equal K for equilibrium. So to say something is in equilibrium for a reaction is to say that the rate of the forward is equal to the rate of the reverse. Not to say that their concentrations are equal, just at that time the rate at which they are moving is equal. So now to connect equilibrium constant to Gibbs free energy, changes in Gibbs free energy is what drives a reaction towards its equilibrium, so to speak. So when we look at, if you were to consider these three graphs that I have here, you can see at equilibrium K, the red K there, and this is, say, this darkened marble, the red marble, represents K as well. You can see that Gibbs free energy is at 0 when it's at equilibrium. Now you have Q where it is the reaction quotient, and basically that's aiming to move towards K, so it can also be equilibrium. So if you kind of see the marble, if you think of it in terms of something kind of going like this, and it's like, okay, the reaction's still going, the reaction's still going, it's like going and going. It's a Q, and it's K, Q, K, K, and it kind of lands there, and it hits its equilibrium. So in terms of where K is, so for this graph, you see K is greater than 1, meaning that the products are being favored. And here for 2, K is less than 1, meaning that K shifted to the left. Up here, K shifted to the right, and K is not shifting in either direction. And Q, in a sense, is always shifting in a sense. So, I'm going to move forward. Well, so let's think about this for a second, actually. So, if K is at equilibrium when delta G equals 0, then you can say that under standard conditions, free energy change for a reaction is directly proportional to the negative of the natural log of the equilibrium constant K. Well, if you look at the equation in green here, as you can see, delta G standard is equal to the negative times the rate times temperature of L and K, which essentially is saying that the more negative the free energy change is, meaning that more negative, that it's more spontaneous, then the larger the equilibrium constant will be. Therefore, the larger, in a sense, the larger the rate, the ratio of the rate forward to the rate reverse will be. So now we're going to tie and Gibbs free energy to entropy. So Gibbs free energy and entropy make a link through spontaneity, and spontaneity is the process that occurs without ongoing outside interventions, and furthermore it's the direction in which, the extent in which a chemical reaction proceeds. And Gibbs free energy is really another force that determines the direction in which a reaction will go, so to speak. So if we look back here and we see negative delta GG, this is kind of being the driving force to bring the chemical equation, the reaction taking place, to its equilibrium. So going back to Gibbs free energy and entropy, if you look at exothermic reactions, enthalpy is negative, so when enthalpy is negative, delta G is likely to be negative too, and therefore that reaction process is going to be spontaneous. So from that point, that being that the reaction is spontaneous, entropy can cause an increase in the randomness or disorder of a system or reaction. So basically, when the change in entropy is positive, it's proportional to that. The change in Gibbs free energy is going to be negative. Thus, this is going to increase the entropy of the universe, which is the whole point of the second law of thermodynamics. So all this with the equilibrium and Gibbs free energy and the rate constant leading to entropy is to increase the disorder in the universe, where so delta S is going to be greater than 0. And that is why most things obey the second law of thermodynamics. So if you think about disorder of life and how a human is born, essentially they move into disorder from as they start from a child, and as they get older, there more and more disorder is happening, so the entropy is increasing, and essentially that's how the world works. And where as your entropy is increasing, your equilibrium is increasing. So when the world will soon, or universe in a sense, because not just the world, not just Earth, the universe will reach a thermal equilibrium, because its Gibbs free energy will reach 0, as well as entropy will be greater than 0, or else it'll pass it. So we can say Gibbs, basically going back to this in we're speaking on spontaneous reactions, Gibbs free energy, when it's negative, represents a spontaneous reaction, and when it's positive, it's going to represent a non-spontaneous reaction. So if we look at this with involving temperature, because temperature is very important in these situations, usually in most cases, a reaction or a process is going to be spontaneous, whether you're at high or low temperature. So for a quick example here, if we're determining spontaneity, you can see we have dinitrogen monoxide, which essentially, produces nitrogen gas and oxygen gas. If the enthalpy is negative and the delta H is positive, essentially we look at that and we go, okay, well then delta G, Gibbs free energy, is negative as well. Since it's negative, it's less than 0, it's creating spontaneous reaction. And even at high temperatures, it's less than 0, it's creating a spontaneous reaction. So Q is going to be the reaction quotient is going to be less than K, and it's going to move to the right. The reactant quotient, is greater than K, it's going to be to the left, and therefore it's creating a spontaneous reaction. So saying that, we can conclude that entropy is increasing. In most cases, entropy is always increasing, even if things are not at standard conditions. Well, thank you for listening, and I hope you gained something from that with a better understanding of the second law of thermodynamics, of entropy, which essentially is the second law of thermodynamics, how Gibbs free energy is directly proportional to entropy and to spontaneous reactions, how equilibrium is driven by Gibbs free energy, and equilibrium constant is very similar to rate constant, or is equal to the rate constant when the rate of the forward is equal to the rate of reverse. Okay, well, thank you for listening. Bye.